Hello, thank you for joining me today. My name is Leo Charlton. I am a technology analyst at IDTechX and the author of the recently published report AI Chips for Edge Applications 2024 to 2034 Artificial Intelligence at the Edge. This webinar, entitled Artificial Intelligence at the Edge, Evolving Homes and Factory Floors, will be based on information that can be found in that report. For those that aren't familiar with IDTechX and what we do, IDTechX is a market research company primarily focused on emerging technologies such as those shown on the slide here. Those include electric vehicles, 3D printing, healthcare, printed electronics, robotics and autonomy, sensors and haptics, wearable technology, and for the purposes of this webinar, or as related to it, semiconductors, computing and AI. We conduct technology assessments and scouting in the creation of our reports, as well as other content which I'll mention in a following slide, as well as company profiling, market sizing and market forecasts. Some of those forecasts I'll discuss in this webinar, as well as strategic advice. What separates IDTechX from the rest of the market research pack, and ultimately why would you want to buy our reports or access our subscription service? Well, there are a few reasons. First of all, we have a deep technical and market understanding. All of the analysts that produce content for IDTechX have a STEM background to at least a first degree level, and more often than not have some experience with the particular topics that they discuss. But as well as that, there's the generational knowledge. We have passed down key industry knowledge since the company's inception some 20 years ago. On top of that, and throughout that time, we have created an extensive network of over 250,000 global contacts, where our primary research is gathered through speaking to people, through interviews, site visits and global event attendance, as well as the being able to look at technology and ask what it does and how it's made. We also connect it to the practicalities. We assess key technologies and applications so as to provide the complete picture of adoption and potential commercialization of the technologies that we talk about. As mentioned previously, the information that this webinar utilizes was drawn from the recently published AI Chips for Edge Applications 2024 to 2034 report. That can be found at the short URL given on this slide. The report includes key forecasts, which are a total forecast for AI chips for edge applications, as well as forecasts in via 6 segmentations, where we have primary regional geographies, so APAC, North America, Europe, rest of world, consumer versus enterprise use, device architectures, wherein there is GPU, CPU, ASIC, DSP and FPGA split outs. There's forecast by packaging type, so that's system on chip, multi-chip, module and 2.5D plus. Application areas, of which there are 3, where we have grouped these by grouped different AI chip capabilities, of which I'll discuss a little bit more as we go through this webinar. But those computer vision, language and predictive, and then 7 industry verticals, of which a few of those I will be discussing in this webinar. We've also conducted surveys of key edge applications for AI, including looking at around 200 smartphones that were released since 2020, around 100 tablets released since that time as well, and the industry leading and competitive AI accelerators and system on chips for automotive ADAS, that's advanced driver assistance systems. The report provides market intelligence concerning AI hardware at the edge, particularly chips used for accelerating machine learning workloads, which includes, as mentioned, the forecast, as well as a review of the technology behind AI chips, the surveys and analyses of those key edge AI applications, and full market characterization for each major edge AI chip product. As well as the reports that we release, IDTechX also have a subscription service. That's a means for users to have more frequent updates between the time it takes for us to publish reports. As you can imagine, that takes a little bit of time to research and get through editorial. So included with the subscription is not just access to certain reports as per the package that's selected, but also company profiles. As I mentioned previously, most of the information we utilize is through speaking to people firsthand, and through interviews with companies we publish profiles as and when those come up. We also attend events throughout the year, so we give highlights and summaries on those events through our subscription portal. We also publish news articles and other articles that might look at different areas such as market landscapes, technologies, etc., that we use to bridge the gap between the time it takes for us to publish successive reports. Further details on subscriptions can be found at the link here. With that introduction now complete, we'll move on to the main purpose of this webinar, which is discussing artificial intelligence at the edge, involving homes and factory floors. This webinar will cover roughly 4 key areas. First, I'll look at AI capabilities, what these are and why they matter at the edge, and then look at forecasts for AI chips at the edge over the next decade. Not all of the forecasts that are presented in the Edge AI chips report that I mentioned, but just the most prescient ones for the purposes of this webinar, and then look at key industry vertical analyses and trends within those key industry verticals. First off, I'll discuss the different computing environments that artificial intelligence can be applied to. On the right hand side, shown here, there's the cloud. The cloud is somewhat synonymous with data centers that comprise servers and racks of AI chips, and those chips are numerous and can be used for both training of AI algorithms and inference. I'll discuss the 2 stages of AI algorithm implementation on a forthcoming slide. Cloud computing and AI within the cloud is not covered in this webinar, and is indeed not a focus of the Edge AI chip report. For more details in that respect, you can look at the AI chips 2023 to 2033 report that was published in May of this year. On the left hand side of the diagram is the edge computing environment. Edge devices can be split into 2 categories depending on who they're intended for and who's buying the devices. Consumer devices, the leftmost branch there, are sold directly to end users, and so are developed with end user requirements in mind. Those can be smartphones and laptops for personal use, for instance. And then enterprise devices, on the other hand, are purchased by businesses or institutions who may have different requirements to the end user and are bought to fulfill the daily operations of running of the companies. Examples of both of these are given on the following slide, and we consider both of these types of edge devices in the Edge AI chips report. There is another type of edge known as telecom edge, and that's given on the right hand side here. Telecom edge resides somewhere between the ultimate edge of the network, so edge devices, and data centers, as telecom edge computing is performed in smaller data centers located as close to the consumer as possible. Typically, the chips that are used for AI purposes in these telecom edge data centers are the same type of chips, high performing, with high power consumption, used in cloud data center computing. This may change over time with greater adoption of the type of chips found in edge devices, but it's that reason, the similarity to AI in a data center, that we don't consider the telecom edge as the true edge, and so don't include this segment in the report and this webinar. Briefly, what are the differences between AI as deployed at the edge and AI as deployed in the cloud? Well, as I mentioned, an edge computing environment is one in which computations are performed on a device, usually the same device on which the data is created, that's at the edge of the network and therefore close to the user. This contrasts with cloud or data center computing, which is at the center of the network. Advantages of AI deployed at the edge on edge devices is that there's a reduced data flow between a central repository, such as the cloud, and the edge device, and that results in fast computation times, preserving bandwidth, reducing latency. Now, some edge devices are still connected via Wi-Fi to central repositories, but in some instances, either where the network connectivity is going to be spotty, and so it's beneficial to have on-device acceleration, or in instances where going back and forth between the central repository is bad because it reduces computation time, such as in automotive instances where low latency is critical to the safety and operation of advanced driver assistance systems. So that's why it's good sometimes to have on-device acceleration. So devices don't have to be cloud connected. The integrated circuit hardware is typically cheaper than data center alternatives as well, due to running at lower powers, because you have to be cognizant of the power supply of the device on which the AI architecture sits. And as data stays in the device, it's often more secure than it would be if it was traveling through a network. Now, there is a flip side to that, in that the data security is dictated by the edge device's security measures. Disadvantages include that AI hardware at the edge typically needs to have lower power consumption than within data centers in accordance with the devices that they are embedded within. So that results in typically simpler toy algorithms being deployed that don't require as much power. And AI models are only as good as the amount of data that is used to train them. So they've got to be trained on a regular basis, and that can mean transferring data from a large number of edge devices to the cloud to provide a large data set. I mentioned before the words training and inference. What does this mean? Well, there are two stages to implementing an AI algorithm. The first is the training stage, and that involves data being fed into the model, whereby the model adjusts its weights until the model has been fit appropriately to the data, avoiding overfitting and underfitting of the data. And that involves, the training step involves performing the same computation millions of times. And so training for leading AI experiments require a rather large number of AI chips to complete this, and therefore they consume a lot of power. For instance, in training the ChatGPT-3 large language model, around 10,000 NVIDIA AI chips, AI GPUs, were deployed. The second stage, once training is complete, is known as inference, and that's where the trained AI algorithm is executed and new data is classified in a manner that's consistent with the acquired data that was processed in the training phase. While speed up of computation is important for both phases, it's most critical in the inference step, as many AI applications require real-time data classification, such as in autonomous vehicles and high-frequency trading. I want to impress at this point that of the two stages, the only stage that occurs on edge devices, as you would expect given the power consumption requirements, is the inference stage. Whereas both training and inference can occur in the cloud environment, in the data center. So when we think of AI on edge devices, we're really thinking of the latter inference stage, where the chip architecture is present on the device, and already trained AI models via software are deployed and accelerated through that chip architecture. When we talk about AI chip capabilities, perhaps that's a little bit of a misnomer, because the chips themselves are there to work especially well and efficiently with AI algorithms, the software. So there's a speed up related to being better able to handle machine learning workloads. Really, we're talking about AI software capabilities, I suppose. So let's just go through these quite quickly. First of all, we've got natural language processing, which is probably the most immediately recognized by the general public now because of the almost water cooler nature of ChatGPT, which is a large language model. NLP is a means of understanding text by using the relationship between different words within the text, where the nuances of context are sought to be understood. The technology would then be able to extract information and insights from the text. As well as their speech recognition, which is slightly different. It's the ability to recognise and transcribe audio in real time, but it's also, you could say, somewhat linked to NLP because they both utilise language. Then you have recommendation and reinforcement learning. Recommendations are a very useful tool for social media and e-commerce sites, as it delivers personalised results to the user through the evaluation of interactions between the user and service items like products and advertisements. And reinforcement learning is not so much in the public eye, but was at the beginning of AI implementation. It's where algorithms can be used to train agents that rival humans for their decision-making abilities, and those algorithms can be used to train agents in games such as Go and chess. Then we have heavyweight and lightweight object detection. It's worth noting that heavyweight and lightweight doesn't refer to the mass of the objects in question that are being detected, but rather the granularity of the masking, the pixel masking that goes over the objects. Whereas you can see, heavyweight object detection really picks out all of the contours of the flower, whereas lightweight just gives a rather more simple boxing around the object. But yes, object detection returns bounding box coordinates for objects in a given range, and image segmentation, on the other hand, assigns an object class to each input image pixel. So basically, object detection specifies where generally an object is, and segmentation gives the object its shape. Object detection, of course, being a crucial component to systems in robotics and autonomous driving. And then finally we have image classification, which is probably the most common task for evaluating machine learning system performance, whereby a classifier selects a class that best describes the contents of a given image and can be used as feature extractors for other computer vision workloads, such as for captioning and style transfer. And so these are some of the devices that employ AI chips, and we'll discuss some of these in this webinar, particularly smartphones, as the early adoption of AI technologies into smartphones, as well as the saturation of smartphones globally, but ongoing premiumization, I'll discuss those terms in a bit more detail, is quite a nice model for the adoption of AI into some consumer products where AI is not completely necessary to their operation, but is definitely a good quality of life improvement over what currently exists, and so those consumer products can contribute to a smart home, a localized environment that's an internet of things in that environment. We also have autonomous vehicles, of course, where, contrasting to smartphones, AI is absolutely necessary for the latter driving levels of ADAS. And then we have the continuous and gradual rollout of AI into Industry 4.0, such as manufacturing line robots and Industry 4 robotics, that we will discuss in more detail. So first off, to give a top-line perspective, this is the AI chips for edge devices forecast, and it should be noted that in this report we have quantified the specific AI architecture on chips and the value related to that AI architecture. So we predict that over the next 10 years, by 2034, the value of the AI architecture that is on edge device chips will be around $22 billion US, with a growth rate of just under 8% over this 10-year period. Now, this line is obviously not an exponential, and it's not steady growth. Rather, it's a complex polynomial, and that's because of a few different styles of growth trends. So as I said before, we've got the saturation for mobile phones, which can be a quite useful model for the rollout of AI that is not absolutely necessary, but a good upgrade in terms of quality for consumer electronics products. saturation in mobile phones globally occurring around 2 years ago, where the need for updating to the latest model every couple of years is not so keenly felt by consumers anymore. And then you've got stepwise growth, such as for automotive applications, and that's because of the need for rigorous safety testing before deployment as you move up the driving levels. And then you've got more conventional continuous growth, as I mentioned, for the rollout of AI into factory floors. So all of these things work together to create this growth line that has bumps and steeper gradients in some parts and less steep gradients in others, where there's a sudden increase because of rollout in certain areas, and then a little bit more of a plateau. When we look at edge consumer versus enterprise edge AI is currently dominated by the consumer market. Though we don't see that changing over the course of the forecast period, we predict that AI for enterprise purposes will experience faster growth than the consumer market. And by the end of 2024, AI chips used for enterprise purposes contribute to just over 20% of the total edge AI chip revenue. That share will exceed 25% by the end of 2034. And there are several important contributing factors to this growth, such as the saturation of smartphones, the large majority of which are bought directly by consumers, the advancement of ADAS technologies and adoption by public transport vehicles, even though, of course, that also affects consumer vehicles, and the possibility afforded by advanced chip technologies to handle more computationally intensive workloads locally, rather than relying as much on the cloud. Here we have the truncated AI chips for edge devices forecast, segmented by industry vertical. The full forecast, of course, is given in the report with related figures per year. And we separate into the 6 key industry verticals for AI at the edge: automotive, consumer electronics, healthcare, industrial, media and advertising, and retail, with another category denoted to cover other verticals with minority share. As of 2024, consumer electronics takes the majority share of market revenue for AI chips at the edge. Where included in this category are consumer products such as smartphones, tablets, laptops, as well as smart home appliances such as voice-activated appliances and home security cameras that utilise AI chips. Industrial, which includes manufacture, and automotive industry verticals contribute the second and third most amounts to revenue. We envision that these three industry verticals will remain dominant up to including 2034. The industry verticals we expect to have the most growth over the forecast period are the automotive, retail and healthcare industry verticals, which have a compound annual growth rate of 12.97%, 10.75% and 10.54% respectively. While the consumer electronics industry vertical is still dominant, due in large part to the expansion of AI into the home, but experiences a slower rate of growth at just over 5% CAGR. So we're going to look at the consumer electronics, which is the highest revenue generating but lowest compound annual growth rate, and the automotive, which has the highest compound annual growth rate, industry verticals in more detail for the remainder of this webinar. AI in the automotive industry takes several forms, where it's not just restricted to in-car systems but can also be employed in the design and manufacturing process line phases of production. For the forecast that we give in this report, we restrict our view of AI to in-car systems, where AI is used for driver assistance as well as in-vehicle entertainment. Where AI is used in production, we consider this a part of the industrial industry vertical. The diagram here shows the typical network of power supplies, sensors and electronics that are used for ADAS, advanced driver assistance systems, features of which include emergency braking, adaptive cruise control and self-parking systems. Also included on the diagram are infotainment displays. So AI chips are found in centrally located microcontrollers, or otherwise known as MCUs, which are connected to peripherals such as sensors and antennae. Onboard AI compute can be used for several purposes, such as driver monitoring, where controls are adjusted for specific drivers, head and body positions are monitored in an attempt to detect drowsiness, and seating positions changed during an accident. It's also used for driver assistance, which is the most necessary or crucial aspect of AI in the vehicle, especially for autonomy, where AI is responsible for object detection and appropriate correction of steering and braking. And then you have a quality of life upgrade, which is in vehicle entertainment, where onboard virtual assistants act much in the same way as on smartphones or in smart appliances. Since its launch in 2014, the SAE levels of driving automation have been the most cited source for driving automation in the automotive industry, which defines the 6 levels of driving automation. These range from level 0, which is no driving automation, up to level 5, which is full driving automation. The current highest state of autonomy in the private automotive industry, where we consider only vehicles for private use and so exclude public transport such as robotaxis, is SAE level 2, with the jump between level 2 and level 3 being significant. Several compute chips that have been and are being designed by the companies are purportedly scalable up to SAE level 5, and this is an issue that companies face when they are making accelerators and system on chips for vehicles, because they know that there's these long rollout times due to safety testing, and which needs to be rigorous for the safety of not only the driver but also other people on the road, other stakeholders involved. And so there's kind of a look towards scalability, so that you don't necessarily have to replace all of the hardware every time you look to address one of these higher milestones of driving automation. I include the Edge AI chips landscape given here because while we restrict this webinar for the purposes of time and also immediate relevance due to the unique characteristics of the industry verticals to automotive and smartphones and tablets within consumer electronics, it's worth noting that there are a whole host of players right now that are addressing various solutions at the edge, and in fact the lists given here are not exhaustive, obviously because of the strictures of trying to fit this all into one slide, but I just want to note them here because the letters next to the company logos refer to the AI silicon that each company designs. So as such, the report on which this webinar is based focuses on the top 3 boxes: the tech giants and systems, the IC vendors, and the hardware startups and new players, which you can read about more about what all of these guys do in the report. I'll now go over briefly how AI is deployed in smartphones and tablets, and I say again that it's very interesting that this is one of the most continuous relatively early adoption of AI architectures into consumer electronics products, because on the face of it, AI isn't particularly necessary to smartphones. We'd still all buy smartphones without the inclusion of AI because of what they fundamentally do and keep us connected. And yet it appears that the inclusion of AI architectures into the system on chips that are included in smartphones is becoming the norm, really. So perhaps the most close-to-hand platform, really, that utilises AI technologies. Smartphones provide a more robust, personalised user experience than ever before because of the inclusion of AI. They include virtual assistants. Most smartphones have virtual assistants either built as part of the operating system or as a separate app. Virtual assistants depend primarily on voice inputs, enabling greater accessibility, which is especially useful for people with motor control and visual impairments. There's smarter cameras, where AI co-processors can be used in smartphones to improve the quality of images and videos taken, and that's done by automatically adjusting the camera settings in accordance with light levels that are hitting the camera. So AI not only allows for better point-and-click shot taking, but also greater functionality. There's improved system functionality, where data is obtained from day-to-day user interactions with the user's device, and it's used by the AI co-processor to determine hardware optimizations, such that the hardware is being used most efficiently for given tasks. So AI compare apps to certain hardware configurations, resulting in a more energy efficient device and therefore extending the battery life. And the inclusion of AI into devices such as smartphones and tablets can make them more aware of their surroundings, as machine learning relies on data taken in via the different types of sensors including in the device. So some devices have certain always-on sensors that allow for the device surroundings to be continuously monitored, such as is the case for user step counts or location tracking, where in both cases recommendations can be made by the device based on the data obtained, and health recommendations in the case of the former, localization recommendations in the case of the latter. And AI can also be used for identification purposes, image to text generation and voice to text generation translation. Now, of course, smartphones are still pretty much all capable of network connectivity, so it's not always necessarily clear where AI acceleration is being utilized via network connectivity through cloud servers, but the fact that there is on-chip AI acceleration, and this is used for improving system functionality and immediately when you access apps like cameras and whatnot, this is very beneficial to the range of functions that is given to consumers. The smart home then is, and this can incorporate smartphones, but it's a growing revenue for AI, given the artificial intelligence, which allows for automation and hands-free access, as well as Wi-Fi connectivity. They're two key technologies for realizing an Internet of Things, where appliances could communicate directly with one another. Some of the devices which can be recognised as smart appliances that comprise a smart home are shown here, and it should be noted that many of the products that a smart home can consist of are consumer electronic in nature, and so we don't include a specific smart home industry vertical in our forecasts. Smartphones and their inclusion of AI and their saturation, although ongoing premiumization, which I'll discuss shortly, provide a pretty good model for technology trends and AI adoption in other consumer electronics products, particularly where AI is not a necessity, but rather seen as a quality improvement. And while smartphone premiumization continues, but saturation at the top end has occurred, the rollout of AI to consumer electronic products for the home continues, and the smart home is not yet fully realised, but we envision that it will gradually become so over the forecast period. Given here is the mobile device chipset market landscape, and you'll notice really that it's quite consolidated now. So on the right hand side we have Apple and Google, and they both produce proprietary chips for use in their own devices. And then you have on the left hand side Qualcomm and MediaTek, that are the two design companies that are really duking it out for all of the other mobile phone brands out there. Now within those two major circles you have Huawei, Oppo and Samsung, but Huawei and Oppo are both Huawei is likely to stop designing chips because of restrictions levied by the US. Oppo has said that they won't anyway because of capital expenditures, and the latest Samsung Galaxy smartphone utilised Qualcomm chips, so it's a bit unclear as to whether Samsung will continue their Exynos chip line for smartphones or look to other avenues for that. For the Exynos chips. So really you're left with four companies, Apple and Google, that make chips for themselves, and Qualcomm and MediaTek. Traditionally, Qualcomm has been effective at cornering off the flagship end of the smartphone market, while MediaTek has come to dominate the low to mid-range smartphone offering. However, there are signs that the status quo may be disrupted over the coming years, as MediaTek have entered into the flagship space with their Dimensity 9000, Dimensity 9200, and most recently their Dimensity 9200 Plus chipsets. But this just shows that over many years of operation, and as the market saturates, we have this quite significant saturation in terms of chip design for smartphones. A total of 196 smartphones released since the beginning of 2020 was surveyed in making this plot and others that are included in the Edge AI Chips report, and the full list of smartphone surveyed can be found in the appendix slides in that report. The plot on this slide shows that the non AI capable, and that means that they don't have included AI specific architectures on the chipsets, have been manufactured in a broader range of node processors, with the highest concentration being between 6 nanometer and 12 nanometer. And the chipsets that don't have AI included architecture are also in the cheapest of the smartphones surveyed. None go above 800 Great British pounds at time of release. Conversely, the node spread for AI capable chipsets is much narrower, with the highest concentration being at the leading edge, 4 nanometer to 5 nanometer, and the AI capable chipsets are also found in the most expensive smartphones, with £1,000 plus smartphones exclusively sporting AI capable chipsets. Smartphone sales started to saturate globally a couple of years ago, but despite saturation, as mentioned, where the need by consumers to update their phones every 2 years not so keenly felt, due to the closing gap between the latest products in terms of technology incorporated. But premiumization is ongoing. Premiumization is where, especially in developing markets, consumers update to the most cutting-edge smartphones available. As such, there's still significant headroom for the mass adoption of premium smartphones that incorporate AI architectures. As new node manufacture processes have been made possible by foundries and integrated device manufacturers, these have been promptly adopted by smartphone system-on-chip vendors, which is especially interesting to see because, again, smartphones don't necessarily require high performance and low latency in how they're used, in comparison at least to other applications such as automotive, that, as we'll see on the next slide, require the most cutting-edge node manufactured processors because performance is key to the correct and robust functioning of ADAS. So yeah, we see that there is a movement here to the most leading-edge nodes, where over 60% of system-on-chips that are found in the smartphones released in 2023 so far have incorporated 4nm chips. This doesn't hold for every application, mind you. I mean, we've talked about smartphones and automotive both needing the most cutting edge, or rather, automotive needing, but mobile phones still adhering to the most cutting edge. Whereas another example is chips for surveillance systems and security cameras, where they have a mix of, if you look at the what's competitive in the industry for these applications, there's a mix of leading edge and more mature nodes. And that depends on a couple of things, such as where analysis of the data collected takes place, whether that be on device or in a server that's connected to multiple surveillance cameras, but also the degree of masking used for detection, whether heavyweight or lightweight, as I mentioned on the AI chip capability slide. System-on-chips for vehicular autonomy have only been around for a relatively short amount of time, but it's clear that there's a trend towards smaller node processors which aid in delivering high performance. This makes sense logically, no pun intended, as high levels of autonomy will necessarily require a greater degree of computation, as the human computational input is effectively outsourced to semiconductor circuitry. So we see that the performance is increasing over time, and therefore, or rather as a cause of this, the need for the most advanced node processors is decreasing to smaller and smaller nodes. And note also that the leftmost y-axis of the graph on the left has a logarithmic scale. So as node size decreases linearly, the performance grows logarithmically, in part because transistor density grows quadratically as the node size is reduced. Moving to smaller node sizes requires more expensive semiconductor manufacturing equipment, particularly at the leading edge, as DUV, deep ultraviolet, and EUV, extreme ultraviolet, lithography machines are used, and more time-consuming manufacture processes. As such, the capital required for foundries to move to more advanced node processors proves a significant barrier to entry to all but a few semiconductor manufacturers. In fact, TSMC, Intel and Samsung are the only semiconductor facilities that can manufacture at 10 nanometers and below. SMIC, a Chinese company, were able to produce 7 nanometer wafers last year, but it's unclear if they'll be able to mass produce at this node, given that they were using stockpiled DUV and repetitive patterning methods. So, as such, there's a trend for IDMs, integrated device manufacturers, that require cutting-edge nodes for their system-on-chips to outsource high-performance chip manufacture to those foundries already capable of such fabrication. So you've got the IDMs on the right-hand side, and when it comes to to manufacture versus design, we see a movement from the right hand side to the left, where actually in the automotive space more companies are involved with design than actual manufacture. So to round off this webinar, I just want to mention or reiterate the key points. So AI, which has long been held in the data center, is undergoing a steady migration to the edge, firstly via consumer electronic products such as smart speakers, smartphones, laptops, and with gradual rollouts to other industries such as automotive and Industry 4.0. Revenue generated by AI chips for edge devices is set to exceed $22 billion by 2034, representing a compound annual growth rate of 7.63% over the 10-year period. And the automotive industry vertical is predicted to have the highest growth rate over the forecast period for edge AI chips at just under 30%, with retail and healthcare trailing. Despite these rapid growths, the consumer electronics industry vertical will continue to be the highest revenue generator, with the inclusion of AI in smart home appliances offsetting the saturation of smartphones and tablets that is occurring at present. I'd like to thank you once again for attending this webinar, and I hope that you have found the information given here illuminating. For any further inquiries, please do feel free to reach out at the email address shown here, and if you'd like to look into more of the details with regards to what is included in the Edge AI Chips report, then please visit the URL shown on screen. Thank you again.